All right, everybody, welcome back, and now welcome to Investigation 7A. Can you believe that we've made it this far into the course? And from what I've been seeing, you're all doing really awesome. So in the last module, or so in the last lab assignment, we talked about what happens to air as it rises. I talked about how it expands and it cools at a set rate, either the dry adiabatic rate for unsaturated parcels or the moist adiabatic rate for saturated parcels. But I didn't really talk a whole lot about what actually allows air to rise. Well, there's actually 4 things that allow air to rise, and we're going to talk about those 4 things today, and then talk a little bit about how they apply to this lab. Okay, so what we are going to do is first we're going to explore the ways that precipitation develops, so ways that we actually are able to get air from the surface higher up to make those clouds, and then we're going to identify areas of heavy and light rain using a Doppler radar. And this is something you've probably seen before. If you haven't, download a weather app and look at a radar image, and I'll show you how to actually identify that. Okay, so first off, how does precipitation form? Well, obviously we know that precipitation forms from clouds. And how do those clouds form? They form from air that rises, expands, cools, and condenses. So just like the cloud in the bottle, when I squeezed the bottle, moisture evaporated, I let go of the bottle, it then cooled and condensed. That's what happens. But what gets that air to rise, cool, and condense? Well, there are actually 4 things that do it. And the 4 things are frontal lifting, lifting near terrain, convergence, and convection. And we're mainly going to focus on the first 2 today, but the other 2 also are pretty important and pretty cool if you ask me. So let's do it. First, let's talk about frontal lifting. So a front is actually a boundary between 2 air masses. You have warm air that's being pushed away, cold air that's advancing, in the case of a cold front. And each of these air masses has different densities. Warm air is very light. Cold air is very dense. And so in the event of frontal lifting, the warm air, whether it's a warm front or a cold front, ends up rising up and over the cold air. And then, as I mentioned, as air rises, it expands, cools, and condenses. Meanwhile, the cold air is rushing in, and it's forcing that warm air up and over. So that's frontal lifting. And in fact, some of the strongest areas of precipitation are usually associated with some kind of frontal system. Usually cold fronts are more intense than warm fronts, and that's just because the cold air pushing in forces the warm air straight up. The second type of lifting, and this is actually one that we experience by my college. I live near Cupertino, which is in the Silicon Valley, and we actually get about half as much rain as our neighbors in Santa Cruz. And the reason why is because of lifting along terrain. So between Santa Cruz and the greater Silicon Valley area, there's a set of mountains aptly named the Santa Cruz Mountains. And wind typically blows from Santa Cruz to Silicon Valley. And the way that works, and so as a result, for the wind to make it from Santa Cruz to Silicon Valley, it actually has to climb up and over those mountains. And as a result, these mountains actually have 2 components to them. The side where the wind is climbing up is what's called the windward side. Windward. Sorry for my terrible writing. This is called the windward side. Meanwhile, on the other hand, the side where the wind is now sinking, where that air is now descending, this is what's called the leeward side. So Santa Cruz, so real quick, leeward. So Santa Cruz Wow, that looks terrible. If you rate me on Rate My Professors, please don't write, drawing on screens look terrible. Or if you do, I don't know it's you. But anyway, so as air travels from Santa Cruz is on the windward side, the side facing the wind, it then travels up the Santa Cruz Mountains. Now we already know as air rises, it does what? It expands, cools, and condenses into clouds. And then raindrops form in those clouds and we get rain. However, then, this was actually from the last exercise, then once that air reaches the top of the mountain, all of that moisture has been wrung out. And so as it lowers on the other side, the moisture is gone now and the air sinks and warms dry adiabatically. And this whole process is what's called the rain shadow effect. The next way that clouds form is via what's called convergence. So imagine an intersection near your house, and let's suppose that every single light at that intersection was green. You would have cars basically colliding in the center of that intersection. That's convergence. So here we have wind actually converging from all directions at this center right here of low pressure. And so wind converges at low pressure. That air then is forced to rise. And then guess what? As it rises, it expands, cools, and condenses. Yay! And then as it expands, cools, and condenses, guess what we get right here? We get clouds. We get clouds. Yes! Well done. So we get clouds. And in fact, if you've ever wondered why, and I wondered this when I was a kid, why does rain fall near low pressure but not near high pressure? Well, this is why, because you get convergence and lifting air near low pressure. However, in high pressure, you get sinking air, and then all of the air, once it reaches the ground, it spreads out in a process called divergence. So convergence forms rain. Divergence does not. Finally, the last one is what's called convection. And convection is basically when air warms near the ground, it then rises. So now there's no other mechanism pushing the air up. There's no front, there's no mountains, there's no topography, there's no low pressure, it's just a normal day. And the air right near the ground gets really hot. And because it becomes really hot, it's able to rise on its own. Then as it rises, it again, you guessed it, expands, cools, condenses, and once it reaches a height where the temperature of the air reaches the dew point temperature, condensation and cloud formation then happens. Now, Terrence, how does this all relate to today's activity? Well, I'm glad you asked. So, in this activity, you're going to be looking at a few weather maps that are related to what's called Doppler Radar, and then identifying areas of precipitation and determining where those areas of precipitation are forming and what's causing them to form. So first, let's talk about Doppler Radar. So we want to know where rain is located. Well, the good news is that we actually have technology that allows us to do that. There's actually this device at a lot of different weather stations, oftentimes stationed on top of a mountain, and what it does is it sends out a pulse of radio waves. And then what happens is that pulse, as it's traveling outwards, it's a certain frequency designed especially to be sensitive to raindrops. And then what happens is the pulse then hits all of the raindrops and bounces back in what's called a return echo. That same device that sent out the pulse also is a sensor for those return echoes. And then the frequency of the return echo, the amount of return echo, and the way that the frequency has changed can all indicate, one, how big are the raindrops, how fast are they falling, where is this all moving? And so that can then help us identify the location and intensity of rainfall. And then all of this information is then plotted on maps that look like this one. And so you notice that on this map, in addition to the fronts that we've looked at before, I will actually go to my laser pointer, the fronts that we've looked at before, low pressures, high pressures, station models, there's actually something else associated on these maps. All of this irregularly shaped blue, green, red, yellow, that's all radar returns. That actually indicates areas of precipitation. And if you actually take a look here, for the most part, precipitation forms along frontal boundaries. And if you notice, areas of high pressure, such as this one here, this one down here, this one over here, and this one over here, are typically rain-free. Whereas areas of low pressure, this one here, this one up here, these over here, little south from this one up here, oftentimes create enough lifted air that if there's enough moisture available, boom, you get rain. Now there are some exceptions to this rule. There's some radar returns over here, and if you actually look at these station models, there is some rain falling at these locations, very likely associated with one of these two fronts. But sometimes the computer will also place a high pressure here, just simply because, hey, it's a little bit higher than the surroundings. We're not going to worry too much about that right now. But for the most part, so just in general, so if you see a question that goes generally, where are these things forming? They're forming around low pressure systems and they're forming along fronts. Now with that said, there are other ways that precipitation can form. Actually, over here, if I were to draw, there's actually a big mountain range here that actually divides much of the western United States from the eastern United States, called the Rocky Mountains. There's actually another major mountain range here called the Cascades, mountain range here called the Sierra Nevada, and another mountain range over here called the Appalachians. Now if you actually take a look at this map, even though there's a high pressure system right here, these locations are actually right in front of the Rocky Mountains. So they're likely getting precipitation caused by air traveling up and over the Rocky Mountains. Meanwhile, the areas down here, very likely rainfall being caused by these local fronts. But also, if you actually look here in California, right there, basically right along the Sierra Nevada, that's where all that rain is falling, right there. And then up here, the Cascade region, there's some rain over there. But yeah, so those are different causes of precipitation formation. And then you're going to see a water vapor image on this lab, and I just wanted to show that the way that the water vapor image works is that typically white represents puffy clouds, black usually represents dry, clear air. And so in this case, you have all of this moisture that's rising up over here. There's actually a cold front right here. And then behind it, we have this dry air. Finally, the last thing you're going to see and be asked questions on is what's called an accumulated precipitation map. And what this does is, using Doppler radar from the past 24 hours, it actually puts together an estimated accumulated precipitation. So how much rainfall did this location get? And the way that it works is that areas in light blue received very little. So areas with no shading, so areas where you actually just see the underlying map, had no precipitation. Areas that have very light blue represented light precipitation, typically between 1/100th and 1/10th. Areas of slightly darker blue between 1/10th and 0.25. Areas of even darker blue between 0.25 and 0.5. Areas of light green between 0.5 and 0.75, and so on and so forth. And so what they're going to ask you is they're going to say, okay, so what areas of heavy rain were there? You're going to look for the areas with the most orange and red. And then they're going to ask you, how much was it? So identify the shading of the darkest red. And then over here, it's going to be somewhere in between these two colors. So for example, if I'm looking over here, it looks like the darkest red is right here. It's kind of that brownish red. And if I'm looking at the scale, in fact, I even see a tiny bit of magenta over here. If I looked at the scale, it would be somewhere between 5 and 6 inches of rain. And actually that really tiny little magenta area would be somewhere between 6 and 8. So that means that the most accumulated precipitation in the last 24 hours was somewhere between 6 and 8 inches of rain. That's a lot of rain. So that's it for this exercise. If you have any questions, comments, concerns, as always, please send me an email. If a question doesn't make sense, also please don't hesitate to reach out. Again, some of these questions can be very terribly worded. So if something doesn't seem clear, or if you have questions about this lecture, please don't hesitate to reach out. I'll see you next time.